Lambda notation represents a function in text format. The format is lambda x dot something. The lambda is a flag that says this is a function. The x dot is the argument list. The rest is the body of the function. There's always exactly one argument. This is called currying. If we had a function with 3 arguments in some other programming language, like function of xyz and something, it would be represented in lambda calculus as lambda x dot lambda y dot lambda z dot something. Note that the body always returns its result, so there is no need for the keyword return. The keyword return is superfluous in lambda calculus. In binary lambda calculus, we can represent the number 0 and the number 1 in the way shown here. We represent 0 as a function which takes 2 arguments, x and y, and it always returns its first argument. We define 1 as another function that takes 2 arguments, x and y, and it always returns its second argument. In pseudocode, we might write function called 0 takes x and y and it returns x. Function called 1 takes an x and y and it always returns y. In binary lambda calculus, we can represent cons and nil as functions. Cons is a function of 3 arguments, x, y, and f, and the body of the function is to construct a function, 2 arguments, x and y, and to return that constructed function. It doesn't actually call the function, it just constructs it. Nil is a function of 2 arguments, x and y, which always returns the second argument. Pictorially, we might write cons takes 3 arguments, x, y, and f, and it returns a function which takes 2 arguments and applies the function f to those 2 arguments. Nil is a function of x and y, and it always returns the y. This usually becomes incestuous and goes much deeper. The parameters are usually functions themselves. Nil takes 2 arguments, both of them functions, so it takes a function of 2 arguments and another function of 2 arguments. Because of the definition of nil, it returns the second argument, which is a function of 2 arguments. In binary lambda calculus, we can represent the bit sequence 0101 as a set of concatenated conses. If we look at this term, cons of 1 of nil, we are actually saying cons of lambda, some argument I'll call A, another argument that I'll call B, and the result is always B, and another functional argument, which I've called C and D, they return D. Note that the third argument, F, remains generic. Hence, the result is yet another function. The function that is returned is basically lambda x dot lambda y dot lambda f, calling the first argument with the arguments x and y, calling the second function with the arguments x and y again, which then reduces on paper to this, and then we can replace this wordy sequence with a shorthand that is basically fxy in parentheses, meaning apply the function f to 2 arguments y and y. There's a fancy name called referential transparency, which basically says we can take syntax that looks like cons 1 of nil and replace it with a different syntax in lambda notation that looks like this, without the quotes. Given that replacement, we can use a text editor to replace all of the instances of cons 1 with nil with instances of replacement text, this stuff. So what's the point of doing all this? Well, for starters, a 1-argument lambda function is like an atom in physics or chemistry. This notation allows us to think about concatenating atoms together to form bigger things like molecules. Nothing is actually different, but the notation allows us to concentrate on one aspect of manipulating atoms. This notation makes it more convenient to write down sequences of concatenated atoms. You can write this stuff in JavaScript, but the result looks like line noise, and makes it messy to think about. If we deconstruct all of our code into tiny Lambda function atoms, then we can use canned text editor rules to crank through the atoms and create various kinds of molecules. We can do this using machines. We could do all of this cranking using paper and pencil and humans to manipulate the paper and pencil and rubber. Or we can machine a bunch of little gears out of metal, or we can use machines that we call computers that make this process a lot easier. Computers allow us to erase our work and try out new ideas at the touch of a button, which is a lot faster than getting someone to erase their scribbles on paper or remachining new bits of metal. Of course, when a piece of code has been deconstructed down into little Lambda function atoms, the code becomes difficult for humans to read. Machines don't care, but humans care. That's when we want to wrap syntax skins over groupings of atoms. We want to lasso lumps of atoms and label them with higher level concepts. This grouping goes on ad infinitum. We eventually want to lasso lumps of higher level concepts and label them with even higher level concepts. Then we want to lasso lumps of even higher level concepts and label them with ultra higher level concepts, and so on, and so on, and so on.